Yeah. So sometimes I feel that perhaps some of the things that I'm going to say will seem very straightforward and simple, but hopefully it will be of some value. So when I was asked to talk here, I think hopefully I said yes quite quickly. And then I started to think about what the meeting was about. I think the main theme perhaps is sparse regularization. So I sat down to try and think, well, what do I know about sparse regularization? And, well, learn't a few things. And I want to describe some of those things to you. I say I know that some of them, and particularly the first little bit, I think will have been known by people very long, everyone here, very long ago. So I think perhaps as a statistician, I will hide behind that for some of my naivety. So I will split it up really into three parts, the middle three bits. But I'd start off by thinking, well, what is sparsity? So, and I suppose, what do I mean by sparsity? Which might be different to what other people, because when I first started to think about it, it felt like there are lots of zeros. Well, I didn't really like that, because I can take a model and some extra parameters which are zero. Does that make it a sparse model? That doesn't seem sensible to me. So perhaps we mean few non-zero parameters. I'm happy with that. Though of course perhaps we have to think about how that relates to the amount of data we have, because we could have a 10-parameter model which fits well to a big data set. We might have a 9-parameter model which fits to a small data set. Which of those is better? So I suppose I thought, well, it's non-zero parameters relative to amount of data. And to me, that's parsimonious. So I did wonder whether sparse is just parsimonious. I did for a moment consider coining the phrase sparsimonious, though I discovered this is in the Urban Dictionary to mean something else. So it's not anything that, but it has a meaning. So to me, a sparse model is perhaps a parsimonious model. I thought about different styles of sparseness. And for this, I'll think of a single object within a region that we're trying to locate. Details are not important. Some approaches perhaps have implicit sparsity, where the data determines that. So we might have a model, it might be a prior, it might be a regularizing function, which encourages sparseness. And perhaps we would end up with a reconstruction that looks something like that. We have regions with nothing going on and regions where things are going on. But a lot of what I do is different to that. Most of what I do is different to that. And perhaps I might call it explicit sparsity because it's determined by the model. So the model imposes sparseness. And we might get a picture that looks like that. It might not be a circle, I just drew that quickly. But we might get something that looks like that. Now, to me, those are both have an element of sparseness. But perhaps this one has several hundred parameters, a few hundred which are zero. This one has a handful of parameters, none of which are zero. But I think those are equally acceptable approaches to what we're trying to do. I don't know whether there is such a phrase, but perhaps the idea of empirical regularization, data-driven, and structural, where it's to do with our model. So I think there's these two types of approaches, at least. Okay, a lot of what I apply statistical methods to is in inverse problems. And the most recent example is in electrical tomography with industrial applications, perhaps for monitoring flow in pipes or that kind of thing. So my notation. There's many different ways of defining things. I think, again, statisticians perhaps a little bit different to other disciplines in just the choice of words. So we have a true function unknown that we're trying to investigate. We measure some data, so in tomography the unknown is inside and the measurements are taken outside. And we have some way of relating the two. And we look to estimate. Well, that's all of what we're doing here, I guess, follows that. But at least that defines my notation. So as a statistician, what I would do is I'd sit down and think about the distributions for each of these parts. And we saw this approach described this morning. So this is perhaps the Bayesian approach. To me, it's just probability modeling with some kind of conditional structure to it. So we have a likelihood, which might be Gaussian, might not be, and we have some likelihood, wherever that's going to come from. And mainly what I'm going to talk about, I suppose, in the first part is that. We have a posterior distribution, and we might maximize it. I suppose, again, as a statistician, I might prefer not to maximize it, but if we have the computational power available, to investigate it in greater detail. So that, in particular, we can, not only confidence statements, but we can test hypotheses and things. So that looks like a very standard setup. And what's in there, of course, if you're not a statistician, you might be much happier at that kind of setup. They're the same, of course. Of course they're the same. It did occur to me over lunch, well, why do some of us talk about maximizing the posterior and some of us talking about minimizing a function like that? It's the same thing that we're doing. But I suppose it's because we think differently. What does that mean? So for just a matrix in there, common choices. Of course, none of these produce sparse regularization, but it took me a while before I'd used other things. I'm very happy with smoothing, but of course that's not always appropriate, and we might want to think of other things. Okay, so there's this direct correspondence between the different quantities. That doesn't, say we're tackling the same problem, so it doesn't get us anywhere, really. So there's this equivalence. Now, when I was digging around for information, I came to realize that actually there's other equivalences, not just between somebody who might say they're a Bayesian and somebody who does, I don't know, penalized least squares, regularized least squares. And many of the things are also equivalent to regression, well, not surprising, and it surprised me a little bit to some of the techniques used in thresholding in wavelets, and possibly thresholding and other techniques. These are just my experiences. And one of the things I thought would be useful to say today is, well, perhaps there's some useful things to learn in these other areas, including for me. I mean, these are perhaps more statistical topics, but I'd not appreciated all of the links. And I learned some new things. Okay, so in the first part, I'm going to use just a simple synthetic test function. So there's mine. It comes from the wavelet literature, but I thought it was an interesting function to try to reconstruct. I put some blur and some noise, arbitrarily chosen values. Well, I wanted not just to show an individual picture, but I wanted to get us perhaps just to see a little bit of movement as well. So what I'll show in a moment, of course, we can reconstruct for different prior parameters, regularizing parameters, and I think it's interesting, perhaps it's an exercise you've all done or you set your students, go away and see what things look like. So just to change the prior parameter and see how the reconstruction changes. So this is just smoothing, of course. I have a few of these. Perhaps I won't show them all, but I think sometimes we learn, because we learn about kind of the sensitivity of our reconstruction and how it depends on these parameters. Well, there's a reasonable, I've not optimized these in any way, there's a reasonable reconstruction, the black on the true red. Follows things reasonably. Now, I suppose I used smoothing for a long time, mainly I use smoothing priors, because they tend to do very well. They're very robust in many ways, and if you have a nice way of choosing the parameter in there, they tend to do quite well. I tried very approximately to use a posterior estimate with a prior on the regularizing parameter to choose these. But I did it rather quickly yesterday, so it's somewhat arbitrarily chosen. Okay, so changing the regularizing matrix doesn't do anything for us in terms of sparseness. So of course, and perhaps I could have jumped a few steps, that we're all used to using some kind of L1 norm for measuring this. But there are other choices. You know, once we say, well, we're not going to use, the first obvious thing is Gaussian. But once we move away from things like that, then why restrict ourselves to an L1? Well, why not something else? And, well, there's a prior distribution corresponding to that. I'm not sure if I said the right thing there. There's a prior distribution corresponding to that. And special cases are obviously there. But there are other values. I think P just has to be non-negative. Well, just for kind of completeness, well, sparse. I managed to get one in the end. But of course, how it gets there isn't at all sparse. So it shrinks, but we don't get anything that's exactly zero. Well, these are all looking rather similar. For a while, I thought to put the same graph in more than once in this. But that's not really the point. L1, well, we're expecting sparseness here. So I'm gradually increasing the parameter. Well, of course, we get these individual measurements going to zero. But, of course, there's nothing in our modeling saying anything about neighboring values. We had lots of things, perhaps it's not an appropriate prior for this truth. There's lots going to zeros, perhaps inappropriately in a few places. So, well, we've seen seen this morning and other times, that it works very well in many situations. But again, it got me thinking. So, going back to the P norm, the prior with that in it. Well, I came across this heavily discussed in the regression and variable selection literature. The Hasty, Tibshirani and Friedman is an excellent place to look for all of these discussions. So there are particular standard values for that with different words. So the P equals 0 case, there you just pick the, I've lost track now, but the best so many variables, best subset. P with 1, the lasso. P is with 2, the quadratic case. Ridge regression. So they're all there. I say slightly surprisingly, I also came to discover, now I think, I wasn't sure about one of those. I think it might be the, no, I don't remember which one it is now. But surprised to discover that really these are the same things in the wavelet thresholding literature. I say, I'm sure and other places, but it's something I know a little bit about. These are the answers you get if you look for the posterior mode, the map, with a prior, as we've seen. So many people apply wavelet thresholding without thinking that they're solving a Bayesian problem. But there's one way of viewing it. So there's all kinds of things. So what I then discovered is there's other versions. So this general p-norm case is, well, bridge regression. And there's a strong suggestion of having p somewhere in the interval 1 to 2. So L1 at one end, L2 at the other end. There's various properties of the prior distribution depending on the value of P, of whether it's convex or not, whether it produces sparse reconstructions or not. And of course that makes the L1 case particularly interesting and easier to find solutions than other sparse versions. People combine these priors. So the elastic net has an L1 and an L2 in it. The fused lasso has an L1 and a smoothing in it. I'd not appreciated that they've been looked at quite extensively, I say in regression situations and elsewhere. So with the top one, so the numerical problems with p less than 1, if you're using some kind of gradient type method, but this mimics that, apparently. The bottom case, what it hopes to do is to set blocks of neighboring values to 0 simultaneously. Okay, so this is the elastic net. Of course, this is quite difficult to deal with because we've now got 2 parameters in there. So what I've done is I've mixed the 2 forms with just some arbitrary mixing proportion and then run it through with a single regularizing parameter multiplying the whole the whole equation. I was just going to do that once more. I don't think it does a wonderful job, but you see the producing a sparse solution in places. So it does seem to do better than my calculations just then for the the straight L1. Well, slightly better. fused lasso, it tends to wobble about a bit, and this is why I think sometimes doing these is interesting. It wobbles about a bit and then suddenly collapses. So there's quite a range of prior parameter, which really, it doesn't change things that much, but once it gets a bit bigger, so that's the fused lasso. Now, I suspect with a bit more control over the relative weighting of the two components, I guess that would improve quite a bit. But I was for the graphs, many of them I did yesterday, so it's my first attempt at some of these graphs. Okay, so that's some comments about choice of prior. The other thing I thought about when I thought sparse is people often say wavelets are sparse. So surely there must be something useful to say. A little bit about wavelets. First, I'll apply it not to an inverse problem, but just to something very simple. So if we were to take the wavelet transform, whatever that is exactly, then we get some wavelet coefficients, some empirical wavelet coefficients, which are noisy versions of the signal. So our wavelet transform of the data is wavelet transform of the signal plus some noise. And there's some nice properties of W, which make lots of the calculations and lots of the theoretical results nice and simple. So the approach then is, well, what we observe, the observed wavelet coefficients, is a noisy version. So let's try and remove the noise, and what goes on is thresholding. So we threshold, or we manipulate in some way, the empirical coefficients, and then invert the wavelet transform to give us an estimate of the unknown. So there's a test function that's without blur, because at the moment we don't know how to deal with that, and there's the wavelet coefficient. So it's another representation, and if you're not familiar with wavelets but are familiar with Fourier methods, then this is rather similar. So we have some wavelet coefficients. Not sparse at all. Not sparse at all. But if we look to threshold those coefficients, that typically means small ones are set to 0 and possibly bigger ones are shrunk towards 0, so our L1 norm type behavior. So it gets quite blocky, like the truth. Oops. Yeah. So there's my guess at a good representation. Well, actually, it's just more or less the standard thresholding rule. And those are our coefficients corresponding to that reconstruction, that estimate. And we have 37 non-zero wavelet coefficients out of an original 256. That seems sparse. But what can we do in the case where we have an inverse problem? So this time, I've taken a linear inverse problem. If we apply the wavelet transform to that, well, what we've got in there is not the wavelet transform of the unknown x, but of h of x, of course. So what can we do? Well, I've not looked at this further. I mean, there is a literature on this, and there is a vagelet-wavelet transform for dealing with this, and a vagelet-wavelet and a wavelet-vagelet. So there are ways of doing it if you know things about h. But what I thought instead was, well, let's put in there our wavelet representation of x. Put that in our objective function, and let's see what happens. So I've put on there L1 prior on the wavelet coefficients. My feeling is it's not only wavelet approaches we could apply this kind of approach to, but any of these kind of dictionary methods where we want to pick out individual components from some dictionary. So let's see what happens. So this is with a particular wavelet, the Debeshe's extremal phase 2. We see at the end, we saw the particular wavelet that's being used, because of course there were very few being added in. So, well, for this example, I don't think that's wonderful. This is the wavelet representation of it. So we now have blur. Blur's back in. We have the same data as we had at the start. And where the black line should be an estimate of the truth, x, the red line. Well, it's got some nasty shapes, and I say that's because of the shape of the wavelet being used. So I thought, well, let's go back to the simplest of the wavelets, the Ha. Okay, that makes it hardly wavelet, but let's see what happens. We have a very blocky function here, so let's see what happens. Okay, of course it goes past the best, but perhaps in there is a good representation. So there's one I picked out as being quite good. So again, the black is the wavelet representation, estimating the red, and that's the set of wavelet coefficients for that. And I think there's 16 or something, 16 non-zero wavelet coefficients. Okay, so that's some thoughts. So I've not used this kind of approach in an example, but it seems a very sensible one to me. Okay, so the kind of final part, the kind of modeling for inverse problems that I do more frequently is some kind of geometric modeling. So let's say that's what I will talk about next. Because I think it is an alternative way of producing a sparse representation. Whether it's sparse in the usual sense or it's a parsimonious model. So very often we do have a strong idea of what we might see. Okay, we need to be careful, etc., etc. But we do have a good idea. You know, and perhaps that's in terms of some kind of hierarchical, geometric description. Very often, a positive side to this, well, perhaps our numerics will be easier, but we may well get out quantities, parameters, which we can use directly. Okay? We don't necessarily want an image as our output of our analysis. We might want a parameter, or a few parameters, that we can use to do something, to control the system, or whatever. You know, if what we have is an image, how is that going to be used for some kind of automatic control? It will need to be analyzed. The reconstructed image would need to be analyzed. So, I think such approach is very problem-specific, which means that every time we come up with a new situation, we're going to have to start again. I should say, because sometimes I forget, this is actually a bit more robust than you'd think. And perhaps I'll touch on that right at the end. But we certainly have to think about our model each time. Even if we say, well, actually, that's quite similar to something I've already done, so I'll just change the model slightly. So this is rather in contrast to what we might call pixel-based, which tend to do a good job very often and are quite robust to the situation we deal with. So, the example that I will briefly describe is one of separating oil and water in a hydrocyclone. This is a rather small case, but as some of you will have probably got first-hand experience, often these are very large things on industrial sites. So, basic principle is, though, that they fire in this case, the oily water into this cone. It causes it to rotate around, and we get oil pushed into the center and the water on the outside. One is drawn off the top, the other off the bottom. It's quite a simple situation to describe. But we want to make sure it's working well. And perhaps we have control over the pressure of the inlet and whatever, I don't know. The height of where we're drawing off the oil at the top, etc., etc. So we might want a simple way of controlling it using some simple parameters. So we might do that just by saying, well, let's say this core has a center. When it's not working very well, it kind of wanders around a little bit. When it's working well, it's kind of locked into the center. So we might want to monitor where that is. That might tell us something about how well we're controlling it. And to measure the size and shape, because that's telling us perhaps something to do with, how much oil we're separating out. Perhaps there'll be other quantities depending on the imaging system here, and I'm in fact using, or mimicking, I suppose, ECT, electrical capacitance tomography. So there might be some capacitances and such like in here as well to be estimated. So we have a model with very few parameters. We have a couple for the center. I'm assuming we've got perhaps a plane of sensors in some critical position, but perhaps we've got multiple planes as well. We've got the center of the core, and we have something describing the size and shape. So, quickly straight to some results, really. So here, the model parameters, well, there's 2 for the center. I'm assuming this is a 2D problem. And a set of radii for a star-shaped object. So I'm not assuming it's a circle. And in fact, in the imagery construction, you can see it's not quite a circle. So this is, again, it's synthetic data, and the truth was a circle. But we're not fitting a circle. So there's something like 18, 20 parameters, I think. I think there might be 16 for the radii, 2 for the center, and perhaps there's 1 or 2 others. And what we get out are estimates or posterior samples, because here I am doing a Markov chain Monte Carlo sampling of the posterior for these quantities. So we've got the center with a histogram to show us the distribution. Credible interval, I've just marked on there, so the equivalent of a confidence interval. Well, there you are, there's electrical conductivity in there. And, well, just for the purposes of a picture, I've taken these 16 radii and averaged them just to put on a picture. But, of course, that could be size. So we get these 18 parameters. It's not an image, but we could turn it into an image. And, of course, that's what's there. Okay. We never need an image. And sometimes people have said, well, don't put one on. People think you're reconstructing images. That's a secondary thing. We have a bunch of parameters, which if we want to draw a picture, we can do. But potentially, we don't have to. So say, here, I'm using Markov chain Monte Carlo. We get a posterior sample, which we can then summarize however we wish. So here's two ways of trying to give an idea of our confidence in where the object is. So this is, I suppose, a credible band. And the idea of a confidence region is that kind of idea. And here are, I don't know, 20 or so samples from the posterior. So I've just picked out randomly 20 from thousands. If we put them all on, you can't see what's going on. So just to give an indication. So they're giving an idea about the changes, the reliability of the estimation of the shape and the size and the position. If they were highly reliable, the band there would be very narrow, and these bits of spaghetti would all be on top of each other. So that picture wrongly gives the impression that we're saying this is the answer and that's it. Okay? We can interrogate the posterior sample to get an idea of variability. Okay, so just about at the end, I'll just kind of say a few final comments. So I've tried to give a flavor of three approaches. Very data-driven, where we have a prior about smoothness or sparsity on individual values. This kind of, well, I put that in very late, this intermediate, and I think the idea of a wavelet representation or other basis functions or other dictionary approaches is kind of intermediate, because you're saying we know something about the shapes of what we expect, but we're then allowing the method to pick out exactly which combination. Or a geometric description. So they're kind of, you know, across the spectrum of different styles. Which is appropriate, then I think, well, depends what we want to do. Whether we want something general purpose with shrinkage or smoothing, whether we want something with a definite model, where, well, as long as we believe that and believe the assumptions we're making, we don't need to make any extra assumptions. And perhaps what I've learned the most by preparing this talk is there's lots of ideas in different disciplines where, well, actually there are ideas which are identical. However, there are some methods that people use in one area that perhaps it's interesting to think about and then apply in other areas. Okay, and that brings me to the end.
Do you know in all this how big is the noise, or how these things vary with respect to how much noise you have?
Clearly, both the amount of blur and the amount of noise are critical in how any of the methods work, I believe. The early pictures, well, I really, both the blur and the noise, I somewhat picked arbitrary values. We have applied some of these ideas to real data. And in fact, including this kind of circle idea to situations where there isn't a lump, it's a more diffuse thing, and they seem to work fine. So these examples, I would say reasonable, both in terms of blur and noise. But clearly, some situations are much noisier than others. Some, the blurring or the whatever the transformation in there is quite different. So I don't have a strong answer to that, really.
The geometric descriptors,
Yes.
those are, so are you are you drawing them from the data? What you've shown, these are samples.
Yes. So
are these priors? This is something I didn't quite.
Yeah. So in that last example,
Yeah.
my model says I have a star-shaped object, so equally spaced angles, and then a radii of whatever length, unknown length as yet length. The center of that is somewhere. So those are my parameters. In some sense, those are my x in my model. It's not a pixel representation or some other representation. My unknowns are those parameters. Well, actually, I suppose there is a prior in that case. I'd forgotten about it, yes. So in that example, there is a prior on what the boundary looks like. So it's kind of smoothness of the boundary. So I'm assuming in that it can't just, they can't be one of the radii juts out enormously or in. But so the parameters, the unknowns of those parameters, they have a prior distribution. Given those parameters, we can work out what data values we could expect for the likelihood, and then it's a posterior estimation, and they're from that posterior distribution.
To really do the estimation, do you basically map this to a pixel prior, or do you otherwise try to...
No, yes, it's something I didn't have time for at all today. In that last case, we used boundary element method. Yeah, so it's not mapped to a mesh and then a finite element, but we're going directly with the boundary element. And I think that's something else that's good, is that sometimes which drives which is perhaps a question, but we can match together perhaps our model with numerical methods for, in this case, solving some partial differential equation. We can match those together, because then that makes our Monte Carlo, well, in the case of boundary element here, then much faster. It really is possible. I won't say we could monitor one of these things real time, but the calculations are then really quick, because we've got a small number of boundary elements compared to thousands of finite elements.
Thank you very much, Robert.
Okay.